Alright, my dear students, so let's look at one more example on page 340, problem 7.19. So if you can see from the questions, you are given a surface current which flowing in positive and negative x directions. So as I told you last time, the best way to draw our diagrams or plane, it depends on the current directions. So since the current now flowing in positive and negative x, so the best plane to be used actually on a YZ plane, right? As shown here, that's why I choose YZ plane, so that we can see clearly the directions of current, right? So now we are given the first current actually flowing in positive x directions, which located at y equal to 1. So if you look at from top view of the x or of the YZ plane, the current will look like a dot, right? Because out of plane. Meanwhile, for the other current over here flowing in negative x directions located at y equal to -1. So again, if you look at from top view of YZ plane, the current will look like a cross because it's coming in, right? It's coming in to the page. Okay, so this is how the current looks like in our case. Now we are required to find the H field anywhere within the regions y equal to 1 until y equal to -1. So anyway, we are going to find the H within these regions. So it's up to you. You want to choose any point. So let's say I would like to choose at this particular point at the origin. Alright, so that's my point of interest. So again, since we are dealing with infinite surface current, so we can actually use the ACL to apply to find the corresponding H field at this particular point. So again, to apply ACL, we need to draw the Amperian loop, which must pass through the point of interest, and then the second one must completely close. Right? So since we have two surface currents, so we have to draw two loops to represent each Amperian loop, right? So let's say, let's start for the first loop. Actually, let's say we start with by this surface current. So I want to draw the loop actually from here, from 0 to that point, stop, and then to next point up there, and then flowing to the next path, and lastly going back to the origin positions. Okay, so that's the loop that actually must pass through the point of interest and also must be completely closed. Alright, this is your first loop for the first surface current. And also we can draw the other loop for here for the second current. Again, the loop must completely close and must again pass through this point of interest. So let me draw again from this path, and then that path and that path. Okay, so that's a loop. It's up to you. So it's better for us to use rectangular loop to simplify, to make it easy for the further analysis. So now, based on our previous last lecture, we have discussed the way how to determine the H direction, right? So again, we can apply the same method to actually approximate or determine the H direction in any region. So let's say I want to find the H field within these regions. So let's take few element current over here. So using your right hand rule, your right hand thumbs represent the current directions, and meanwhile the other right hand fingers represent the H directions. So if you use your right hand rule, you can see that the H field that actually propagate within this region actually in negative z directions. And also for the other side out over here, you can see that the H field will go in positive H directions. Okay, so that's the H field that actually appear within these two different regions. Okay, so we know that the H field within this region flowing in negative, and again also same thing for here, the H field will go in same in negative H directions, negative Z directions. And also for here again we have the H field will go in positive Z directions. So that's a direction that we can find using the right hand rules. So okay, so now before we proceed to the ACL, we need to actually label or denote the H to make it easy our analysis, and the number of H actually will follow the directions of H. So let's say I want to focus on the first loop over here. So since the H actually coming down, so if I choose this one become my first H, so that's going to be your second H, right? It must follow the H direction, so that's going to be the directions. And also here we're gonna 3, and that's going to be your second arrow of second path, and then here is going to be your fourth H, and again that path, that arrow, and lastly that arrow from 4 to 1. So that's going to be our close rotations, okay, of the loop. Likewise for the left hand side loop here, you can see also you must actually draw the H or label the H based on the H directions. Okay, so now let's focus on one side only. So based on this loop, we know that we have 4 paths, whereby we have to decompose the ACL equation into 4 different paths of integrations. From here, close integral H dot dl equal to I enclosed, and this is our third Maxwell equation in terms of integral. Okay, so now let's split into 4. So the first one here from point 1 to point 2 here, right? And here was one have H dot dl number 1 for the first path, let's say, and then plus the second path from 2 to 3, this path, again the H dot dl number 2, and then plus for the third path from 3 to 4, again H dl number 3, which is for path number 3. And then lastly, our last path, which is from point 4 to point 1, 4 to 1, and here we have H dot dl number 4 and equal to the I enclosed. We hold on first, we just focus now the Ampere loop path. Okay, so that's our Ampere loop path. So now let's analyze one by one. If you see from the first path, actually the flowing from 1 to 2, so this path guy actually lies in this region. So we know that the H that exists within this path only exists in negative Z direction. So you can simply change here, become negative H Z directions. And if you calculate for the DL, right guys, this the path here guys actually lies on the Z axis, so you also can simply change this DL become Z dz. Don't care about the sign, just take the DL, because we're going to take the sign based on the limit afterwards, not now. Okay, now look at the second path, which is from point 2 to point 3, and we can see guys from this path we know that there are 2 H direction appear. So for this left hand side, the H in negative direction, and for the this right hand side, the H in a positive H direction. So you can simply change this H become positive, negative H in Z directions. And now the path guys for 2 to 3 now lies along the Y axis, so you can simply change this Y DL become Y dy. Okay, now let's do the next part. Now path from 3 to 4, this region, right, the only H field actually appear in positive H z direction, so we can simply change this H become positive z directions, and then again the path here lies along the z direction, z axis, so you can simply put z dz. And last path from point 4 to point 1, again this path guys covering two regions. The first one over here which have positive hz directions, and the other one over here having a negative h in z direction, so you can simply change this h here become positive negative hz z directions, z directions. And again now guys, the path here lies along the y-axis, so you can simply change this dl becomes y dy. Agree? So let's do dot product between the h and the l. From here we know that the z dot z, yes, we have value. Okay, now here z dot y gonna have 0 value based on dot product. And again here z dot z we have value, and lastly z dot y also will have 0 value. Alright, okay, let's proceed putting the limit. So now for the first path, right, from 1 to 2, here we have a negative hz z directions dot z dz for the first part, right? So now look at carefully. Let's say I assume that this loop has a height of h, right? Let's say we assume it has height of h. So now you can see, let's look at the directions. Now this point 1 has a height of h to 0. Now h to 0 because the height is h. Now the flowing directions actually from 1 to 2, and 1 here has h and 2 here is actually a 0, so the limit become h to 0 plus second path from here from 3 to 4. Again guys, from 3 to 4 the limit actually from 0 to h, because at 3 the value is 0, at 4 here the value is h, so now I can put 0 to h and now put the value of positive hz as shown here dot z dz. Okay, and now we have to find the I enclosed within this loop. So if you see clearly, the current only exists between z equal to 0 until z equal to h, so you can simply integrate. So the js number 1 dl, which the limit from 0 to h. Alright, so if you proceed, we can have this final answer. We have hz h plus hz h is equal to js1 h. So finally going to have this h in z component become half js1. Alright, so if you look at carefully, the value of js1 here is 20, right? So now this refers to the magnitude only, there's no vector, so just take 20. We're gonna have here become 20 over 2 equal to 10 ampere per meter. Okay, if I want to know the direction, so we can see that from this diagram, at this particular point the h axis appear in negative z, right? So you can simply put in this form, the h become negative 10 Z ampere per meter. So that's how we find the H in a vector. So based on the direction that we have earlier in this diagram. Alright, how do we check this answer is correct or not? So you can simply check your answer using the simple equation shown here, which is the H can be found using these equations. Half JS cross AN. So now I want to calculate the H that due to the first current. So let's say just I define as number 1. So now become JS number 1, also AN number 1. Okay, so now we deal totally in vector. So JS1 actually given in positive 20x, right? So just put here positive 20x cross the AN. Okay guys, the AN here actually refers to the unit normal vector that pointing normal from surface current to the point of interest. So this is our surface current side, and then this is your point of interest. So AN must point normal from surface to the point of interest. So that should be your AN number 1. Again, must point normal from surface to the point of interest. So that should be your direction. So in this case, we know that the AN1 is equal to the negative y. Right? It got against the y-axis. So now we have here negative y. So if you do cross product between x and y here, negative y, you will have finally the answer become a negative z. So finally you're gonna have here the H that due to first current equal to negative 10 Z ampere per meter, exactly same as shown previously using this technique or method. So again here this H1 is 10 Z ampere per meter. So guys, likewise you also can find the H number 2 that due to the second current over here. If you redo all the same process, same method, you are going to find the H number 2 again, which equal to negative 10 Z ampere per meter. Okay, so let's check our result using this formula. So the H2 half, and now the GS here now in negative x direction. So just put here negative 20 x direction times the n number 2. Again guys, the n must always point from surface to the current of interest. So that's your surface and that's your point of interest. So it should be an will point to that way. That's going to be your an number 2, which is in positive y direction. Okay, so now here we have positive y, and again you are going to have same result equal to negative 10 Z ampere per meter. So now we have two value of H1 and H2, and finally you can have the total H that actually appear at within this region by combining the two H value. So the total H actually H1 is plus to the H2, which equal to negative 20 Z directions ampere per meter. Alright guys, so that's the way, or that's the idea how we can solve these problems using ACL. I hope you can try yourself and make sure you really understand the flow of using the ACL. And you must know that in this problem we can use either approach. You can use two methods. The first one, you can go through all this lengthy process, but very useful and very good for you to know. Or also you can just shortcut your process by applying this simple equation to find the H field due to the infinitely large surface current density. So bear in mind that this equation only applicable to the infinite surface current and not applicable to finite surface current. Okay, so make sure you use the correct formula for the right time and for the right case. Okay, so guys, thank you and all the best for your study.